Hello everyone, welcome back. In this video, I want to finish our discussion of double integrals over regions of type 1 and type 2, by discussing some properties of double integrals. The first comment I want to make is that when we talked about, in the previous video, when we talked about changing limits of integration, it's sometimes easier to do one order than the other, but sometimes changing limits of integration is so essential that I would not be able to compute this integral in particular without changing limits. Because if I was going to start with the limits of integration as they are indicated here, the very first thing I would have to do is solve the integral of sine of y squared dy, and this integral is what we call a non-elementary integral, in that this function does not have any elementary antiderivative. So I can't find this exactly. So unless I was going to do some numerical integration of this integral, I'm not going to be able to solve it as is. But it turns out that you can solve it if you change the limits of integration. I'm going to be posting in this playlist a different video specifically about this integral, so I'm not going to talk more about this, but I will just leave it as an exercise. Take this integral, change the limits of integration, and then you'll see that you'll be able to solve this integral. Now, double integrals over regions of type 1, type 2 satisfy the same properties that even the single variable integral satisfied. For example, that the integral of a sum of two functions is the sum of the integrals, or that the integral of a constant times a function is the constant times the integral of the function over that region. We also can have inequalities. So if f is always bigger than g in the domain for all points in the domain, then the integral over f will be bigger or equal to the integral over g. Sometimes this is useful to give estimates of integrals when we do not know how to compute this, but we know how to compute something a little bit easier that is bounded from below. Then I can compute this just to give estimates for my functions. We'll see an example of this in a moment. Another property is that if I have a domain, that a region where I'm going to integrate, and I can split it into two separate regions such that D is the union of those two regions, then the sum, or the integral over the big region, is the sum of the two integrals, the integral over one region plus the integral of the other region. This is again useful sometimes when, for whatever reason, we can easier integrate the function over these two sections of the region, instead of trying to integrate over the entire region all at once. Another property that is useful is that you can compute areas of regions with double integrals. That is because if I have a region, say, I have some region, let me just draw it here. This is my region D in the xy plane. Then if I compute the value of the function 1, the integral of the function 1 in that region, well, that will mean I cut out the plane 1 above it, and then what's going to happen is that there's going to be sort of like a copy of the region up here, and I'm just going to get a cylinder that has the shape of the region. It's of height 1, and the base is area, the same area as the region D. So the volume of this whole thing will be the area of D times 1, which is the area of D. But on the other hand, I can compute the volume of this object by computing the integral above the region D of the function 1 dA. That will be the volume, and the volume will be the area. So we have this equality. So I can compute areas of regions by computing these sort of double integrals. Finally, another application to doing bounds is the following. Let me draw this in a different way. So suppose I have now my region is, let me just, for simplicity, that I have a circle in here, and there's going to be some function above it. So some function takes values over the circle, right? And then there will be some maximum value, say the maximum is here, some minimum is here, and I want to estimate what is the volume of the object above my circle and below the graph, well, what I can do is, well, simply capture two cylinders. So I can put a cylinder at the minimum level like this, and I can put another cylinder that is at the maximum level. And then the difference of the cylinders, it will be that, well, the volume is, this volume of what I want is smaller than the volume of the larger cylinder, and it will be larger than the volume of the smaller cylinder. And that is exactly what's happening here. If I have a function and I have a minimum value and a maximum value in the region D, then this is the volume of the cylinder that is contained in the volume that we're trying to find out. And this is the volume of a cylinder that contains the entire shape we're trying to figure out a volume of. And this is the volume that I'm trying to figure out. So these inequalities tell me that I can estimate that volume using these two volumes. So let me show you an application of that method in this case. So I'm trying to integrate this function. I'm trying to figure out what is the volume under the graph in this case. So I do have here a circle of radius 1 in the xy plane. So the region is a circle of radius 1. So here is 1, here is 1. And then I have my function. My function, by the way, it's the bell curve, but in 3D essentially. So it just goes like this and like this and like this and like this. So the cross sections or the level curves are circles, and they're sitting above a circle. And I want to compute what is the volume above the circle of radius 1 for that bell curve that would have applications in probability, for example. So what I can do is fit this into two different cylinders. So if I find the maximum value of my function, then I can fit the whole picture in a cylinder. And also, if I find the minimum value of the function, I can fit another cylinder below it. So I know that the graph, the volume of the graph, will be between the volumes of those two cylinders. So what I actually need is to know what is the maximum value of f of x y e to the minus x squared plus y squared, and also what is the minimum value of this function in the region R. So in the circle of radius 1. So in the circle, and this is the filled end circle, so it is the entire region that is within the circle of radius 1. And well, you can use the methods we've seen before. So our previous methods can actually show that there is a local max. So you can figure out where the critical points are, and there is only one critical point at 0, 0. And this is, in fact, a local max. By taking derivatives and second derivative method, we can figure out that this is the local max. So what is f of 0, 0? That's e to the minus 0 squared plus 0 squared. So that is e to the minus 0. So that is just 1. And now what is the minimum? The minimum will actually happen in the boundary, because it's decreasing everywhere from that local max. There's only one local max. It's decreasing everywhere. The minimum happens in the boundary, and the boundary is when x squared plus y squared is equal to 1. And in the boundary, f of xy will be, let me do this in the next page. So f of xy, which is e to the minus x squared plus y squared, is equal to, when we are precisely in the boundary, we are when x squared plus y squared is equal to 1. So it's e to the minus 1, which is 1 over e. So this is the minimum value of the function in the region. So now the integral in the region of this function that I don't know yet how to integrate will be at most the largest value of the function, which was 1, times the area of the region. The region was the circle of radius 1 filled in. So the area of the region is just pi r squared. So it's pi times 1 squared. So it is pi. So it is the entire integral is less or equal to pi, and it is bigger than the value of the minimum value of the function times the area of the region, which is pi. So what we get at the end is that the value of the integral I'm trying to estimate over that region R is less or equal to pi and bigger or equal to pi divided by e. So that gives me inequalities so that I can have some estimate of what is the value of that integral without actually having to compute the integral itself. So in the next video, we're going to move on and try to start doing integrals, but in polar